this experiment because it kind of explains how quantum mechanics works in terms of probabilities and so on. So ignore this for a minute. So we've got an experiment where you've got a laser and it fires light through what's called a half-silvered mirror. And the half-silvered mirror is something that lets half of the light through one way and half the light through the other way. And these are normal mirrors. So the light will go this way, bounce off the normal mirror, and then we've got another half-silvered mirror. It can go 50% this way, 50% that way. Half of the light that way, half of that way. So what you would expect to happen is, well, half of the light will be in this detector, and half of the light will be in this detector. But these lengths here, they are not exactly the same. These paths are like one would be slightly longer than the other. So you would expect all of, so let's say you send a single photon through. Single photon can go through this path here, and then it can go either that way or that way. So you would expect either the whole amount of the light to go into one detector or the other. But that's not the case. What's actually measured is a combination of the paths, this way and this way. So we have, so Born's rule is one of the most important parts of quantum mechanics. Let's write it as with Schrodinger's equation. So if you want to work out the probability, let's say in the example of a Schrodinger equation about where's the position of what's the energy of an electron, the probability of an electron being at a certain energy is equal to the wave function, in that case, the magnitude of the wave function squared. Now that's Born's rule, but it's a simple rule from probabilities. If you have something called a probability amplitude, A1, you take the magnitude of that squared, you'll get the probability of whatever that event is. So, and the way, when you have multiple paths and you can't tell which way it's going, then you add up the probability amplitudes, then take the magnitude, then square it, and it will give you the probability. If you do this separately, let's say you took the probability amplitude of this path and squared that, and then added it to this path and then squared that, you would work out a wrong number. It would be too much. You know, it wouldn't give you the probability. It would give you the probability of doing. It would give you the probability of, if you blocked this one and measured the amount of photons, counted the amount of photons, and then you blocked this one and you measured the number of photons at each detector. That would give you the answer. This one gives you the answer of the single experiment. How many go to this and how many go to this with neither blocked. And this is analogous to the double slit experiment where an electron can go one way or it can go that way. It can go through one hole or it can go through another hole. If you took the probability amplitude of going through one of the slits compared to the other one, and then took the magnitude and squared it, and then added it to the magnitude squared of the other one, you would get you would get the equivalent of if you blocked one of the slits and you measured all the photons going through, and then you blocked all the other slits and measured all the photons going through. So you don't get the correct answer. The only way to get the correct answer is adding the probability amplitudes of going through each possibility. And in this case, we have to add up the probability amplitudes of going through this path to the detectors and this path to the detectors. And once you add those up, you get the correct answer for the probabilities when you start moving these mirrors around to put them out of phase and in a phase with the other path. So if you send a single photon through this system, you classically you would expect it to take one route. It wouldn't interfere with itself because it can't, because it's one thing, and it would arrive there. And then you would calculate another, maybe it goes the other way and it arrives there. But that's not what happens under experiment. What happens is the photon acts in superposition of both of these possibilities, and then when you detect it at each detector based on an interference. So a single photon is not if a single photon can interfere with itself, it's not, you can't treat it like a physical object. You have to treat it like you don't know which path it went through, so it's in a superposition of both paths. And it's not that we don't know because our eyes can't see it because it moves too fast or it's too small. We cannot know. It's you cannot know without measuring it, and as soon as you measure it, the wave function collapses. So if you measure it here, the wave function collapses at this point, but the wave function has been through both of these paths. So you have to add up the possibilities of for each path, and then you'll get the correct percentages of each possibility. And this counts for anything. This is an example of photons, but the same applies for energies. Like if an electron has a possibility of two energy levels, that you can essentially work out the probability amplitudes of them, and you can find, well, what's the chance it will be, if I measure it, it will be in this amplitude or this amplitude. So this is a general principle for all quantum mechanics, but this is particularly interesting because it shows that even a single electron cannot be thought of as hitting the wall going through a single path. It goes through both paths, or all paths if there's more than two, in a superposition, and you can add them up, the probability amplitudes, add them up and square it to get the probability of it going into one detector or another. So you could take the photon, what's the probability of going through here, what's the probability of going through here, this way, into each detector. And once you get those, you can figure out what's the probability of it going through one of the detectors. This is very similar to the double slit experiment, where it is essentially analogous to the double slit experiment, and it has a kind of, because of you moving the mirrors, you can see experimentally how a single photon doesn't act as a physical object but acts as a wave function that interferes with itself. So if you have a double slit experiment and you fire a single photon, a single electron, let's say, if it goes that way and stays there, or that way and stays there, it would not interfere with itself. So, like, let's say it goes through here, lands there, lands there. It would not have an interference pattern because you can see the path. It's going through here and it's landing there. It's going through here and it's landing there. But what actually happens is a single electron wave function will go through both of the slits. It will interfere with itself, and as the electrons hit the wall, you'll see the interference bands build up on the wall, where like it's most likely to be constructive interference at the center. Then there's a band of destructive interference where the single electron waves interfere with each other, so that this area is destructive, is interfered with destructively, and the electron very low probability of hitting it, and then a little smaller probability, and then so on. So you just get a standard interference pattern. So if a single electron it acts in superposition, then you have to use this way of finding the probability of where it will be, and you have to treat it as if it isn't a physical object, but it is in superposition of all the possibilities until you measure it. Once you measure it, the wave function collapses and you can forget about it. But until you measure it, you have to. So let's say I blocked. Let's say I measured it. I blocked this and I measured it here. So it only has one path to go through. I'll measure it here, and it will be, and then it will continue through here, 50-50 chance each way, and there's no alternative to that because it has been measured here. But if I measure it here, I have to allow for these hidden paths that I can't see, and because of that, that gives you an idea of what the quantum world looks like. So if you take the double slit experiment again. It's a bit hard to draw, I would think, but let's take the double slit experiment and a wall. So if we think of a single electron, it's not actually, so we know it's not a ball. We know it's not going to go through this path and hit the wall. We know that isn't going to happen now, because that previous experiment on its has shown that, and we know that that's not how an electron acts. So the electron it's more like a wave function that hits both of these, is influenced by both, and it ends up as a wave function of intensities, where there's most of it's there, then a little bit there, hits there, then a few of them hit there, and they interfere with each other. So you can think of this as like a wave as it approaches it. We haven't measured it. If we measured it here, then then it couldn't possibly go through this possibility anymore. So you've wiped it out. If we block one of these, there's no interference because there's only one possibility. There's only one possibility for it to go through, and that's one. But if you leave them open, the wave will come through here, interfere with itself, and when we measure it, this is where we measure it, at the wall, where we measure it. Once we measure it in a place, and it has the most probability of being here in the middle, and then a little bit there, and then very little at the edges. And then there will be these points in between where it destructively interferes, and you maybe don't detect any, because the wave completely, as it goes through here, it completely forms it interferes destructively, and you'll never detect it there. And these would have probability amplitudes, because these are two different possibilities, and how that affects. In this case, it's symmetric, but in that other case, it wasn't symmetric. You could have had many photons at one detector and barely any at the others. In this case, it's symmetric, but you can imagine experiments where they make one of these bigger width, things like that, or make the wall not equal distance, things like that. You can change it so that these probability amplitudes aren't the same, but in this case, they're the same, and so it's symmetrical, But so that's how you should look at the world. You shouldn't look at electrons as physical objects. You should look at them as wave functions that will take all of the possibilities that they have at their hand, and all of the interfering possibilities and the environment they're in, and once you measure it, then the wave function collapses. But until you measure it, the wave function exists going through. So there's a very different view to classical mechanics, because you can no longer think of this as a gun shooting electrons or photons, shooting electrons through here, and they arrive at different points and don't interfere with each other. A single electron has a wave function that has interference in it. And that's a very important part of quantum mechanics.